Welcome to the Electrical and Computer Engineering session of ESEC 2019. My name is Andres Lombo. I'm a second-year engineering science student. Today, I have the privilege of introducing Professor Vivienne Sze. How many people can say they have won an Emmy Award for their engineering work? Well, Professor Sze can. As part of the joint collaborative team on video coding, she developed the high-efficiency video coding standard that is now being adopted by all ultra-high-definition television distribution channels. For this brilliant work, she won an Engineering Emmy Award at the Television Academy's recent 69th Emmy Engineering ceremony in Hollywood. Professor Sze received a bachelor's degree from the University of Toronto in 2004, the master's and the PhD degrees in 2006 and 2010, respectively, from MIT. Today, Prof. Sze is the head of the Energy Efficient Multimedia Systems Group at MIT. She develops high-performance systems that balance power, speed, and quality for applications ranging from computer vision, deep learning, autonomous navigation, and even video compression. Now, with a warm round of applause, let us now welcome Professor Vivienne Sze.
All right. Thank you very much, Andres, for the introduction. So I'm very happy to be here back at my alma mater to talk a little bit about the research that we've been doing and also my career trajectory to where I am today. So today we're really focusing on efficient computing. I know this is the ECE, so Electrical and Computer Engineering session. And so what I really actually want to show you is that with ECE, you can intersect a lot of the different topics that we're hearing about today. So Andreas already mentioned some of my work on video, so I'll talk a little bit about that. We also intersect in AI, in robotics, and in healthcare. So what we really want to show is the importance of ECE, and in particular, efficient computing and how you can make an impact with that. And of course, before I begin, I want to acknowledge all the collaborators I've had over the years who have contributed to this work. This includes my students and my co-PIs in a lot of the projects. So to start off, I'll just mention, so I grew up here in Toronto, so this is really coming home for me. As growing up, I really loved television and movies, and you'll see how that kind of, that thread kind of weaves through with my entire experience. One of my first experiences related to kind of research related to image processing was in high school. So in high school, I had a co-op position at Princess Margaret Hospital where I got involved in looking at 3D image reconstruction. This is with Professor Peter Ottensmeyer. Let me turn this on. Here. And so basically what this job was, this is what it was probably around my fourth year. So I was a senior or fourth year in high school, so grade 12. And so we were looking at taking these 2D images that you can get from these electron microscopes and then rendering them into a 3D reconstruction. And the benefit for this is that you can actually have a better understanding of these proteins, and you can understand how they might be intercepted, and this could lead toward better anti-cancer therapies. Right? So if you understand the structure of these proteins, you can understand how they might interact with different drugs. And so I found this to be very amazing, that with just some simple image processing, you can really have impact in the health space. So for my undergraduate degree, I was very interested in working with image processing, so I selected electrical and computer engineering. And so I just want to emphasize that back then, the types of images that we were dealing with were very different. So this is my class in the fall of 2001 in front of the MIE building. And so the types of devices that we were using back then were things like film cameras. You still have to take it to shoppers to get your films developed, and you couldn't take a whole bunch of these images. You could only take one, and you have to wait to see what you got. And even during that time, around 2002, that's when the first kind of photo camera, or camera with an actual phone with an actual camera came out, right? And there, the display of this phone was very small. We're talking about 132 by 176 pixels. The maximum resolution you can capture was basically VGA 480 by 640, right? So this is a very different era back then. But still, I was very interested in image processing. And so in terms of taking classes, we got a very broad kind of foundation in ECE. So we took a lot of courses related to signals and systems, for example. So that's kind of the foundation of image processing. You start learning about things like convolution, image transforming signals, but also because of the very broad base, we also had to take circuits. So these textbooks may be familiar with you, so we used Oppenheim-Wilsky for signals and systems, and then Sedra and Smith for circuits. Then around third year, I decided maybe I wanted to try PY just because I wanted to figure out what I wanted to do after I graduated. So during that time, actually, as it turns out in that era, there were actually no real internships in the signal processing field. So though I was really interested in that, there were no opportunities there. Most of the opportunities are actually in circuit design. And in particular, the big company that was hiring at the time was ATI. And there was also this startup by two professors here at University of Toronto called Snowbush. These are now known more as AMD because AMD acquired ATI, and then Snowbush was acquired by Genum, which was then acquired by Semtech, which was then acquired by Rambus. So you might know it as Rambus today. So I would say thanks to the broad education of knowing circuits as well, I ended up going to Snowbush. So again, this was a startup started by Professor Dave Johns and Ken Martin. You might know them from their analog integrated circuits design textbook. So this was my real first exposure at both the startup experience as well as industry design experience. What they really did there was build these analog mixed signal circuits. So what that actually means is, most of the signals we have in the world are analog, and so you need to convert them into some digital format before you can process them. In particular, so they built circuits for that. One particular project that was kind of cool was at the time this power line communications. So back then, Wi-Fi was not a big thing yet, so that they were trying to think about how do you get internet into all the different rooms. And there was an idea where you can use the actual power line, so from the different plugs where you plug in to get power, could you also transmit information on those lines as well, right? So that was one of the interesting projects that we learned there. So during that time, it's because it's a small company, they gave me a lot of responsibility. I ended up being in charge of a lot of the physical design, which means basically transmitting or translating, these circuit designs into actual physical layouts of chips, which would then be sent out to be fabricated into IC chips. And we ended up doing several tapeouts, 4 tapeouts during the 16 months I was there. The nice thing about joining a startup was that there was a lot of responsibility. So it was only a 10-person company at the time, so there's a lot of opportunity to grow and learn, but it was also, of course, a lot of work. By the time I left the internship, it grew to 20 people, and I think it's at least like 50 to 100 people now, so it's much larger. So the one thing that did stand out to me is that while I was working there, most of the technical employees had either a master's or a PhD degree. Actually, they were mostly Ken and Dave's students. And so that made me decide, well, if I want to kind of do more of this design work, I really should think about applying to grad school. So that's what really motivated me to apply in 4th year. And then I graduated in 2004. So after I graduated from undergrad, I ended up going to MIT. And one of the first projects that I worked on for my master's program was looking at low power ultra wideband. So what that actually means is at the time, normally, if you're transmitting, there are 2 ways to transmit signal. You can transmit it at a very narrow frequency, which is what we typically do. But you could also, in theory, but you would have to narrow band to transmit at very highish power. You could also have a wider band and spread it across multiple frequencies, but then you can transmit at much lower power. Right, and this had applications looking at wireless communications in the near range for different devices. So for example, to avoid having to plug in USB connectors everywhere, could you do wireless transmission at very high rates but very close by? So now I'll get a little bit into the technical stuff. So what was one of the key ideas that we exploited in order to enable low power processing for this type of communication? Well, the key idea was to trade off what we call power consumption with parallelism. So the idea, if you guys remember back in your physics classes or basic electrical engineering classes, is that basically where does power consumption go? It's a product of the capacitance of the circuit that you're switching, the voltage, how much you have to switch it by to charge it up and charge it down, and the frequency at which you're switching it. Right? And so what it turns out is that as I reduce the supply voltage, right, I actually quadratically reduce the power consumption, right? And similarly for energy per operation, if I reduce voltage, I can reduce the energy per operation. So changing the voltage is a very effective knob in terms of reducing energy consumption. And this is something that was developed by my advisor, Anantha Kasan at MIT, who discovered this knob that we could really use for designing circuits. And so the idea here is that if I want to operate at, let's say, what we would call the minimum energy point, the lowest energy consumption, you want to operate at a lower voltage. And this is for, it goes up here because of leakage energy, but let's not get into that. But basically, you want to operate down here. Now, the challenge for that is if you want to operate at this lower voltage, the delays of your circuits become much slower, right? So you might be consuming less energy, but you're going much, much slower, right? And so that's a problem when you have applications where time matters. So we're soon going to start talking about video, and so imagine you need to watch video at 30 frames per second. You don't want to go slower than that, right? So you need to do something to combat this delay, and so the idea here was that so just to emphasize delay, if I go operate at low voltage, I would take twice the time operating at this low voltage. So how can I address this? Well, we can use what we call parallelism and pipelining. So can we do more operations at the same time, right? And so at the end of the, at the end of the time limit, you've completed the same number of operations, but you've consumed less energy. And this is in principle somewhat how these multi-core systems work, right? You're doing more things in parallel, but now you can operate at lower power. And so as a result, by doing this, you can get a 5x power reduction. Okay, so this was looking at, as I mentioned, it was looking at processing related to communications, but really, from my interest, I really wanted to work on video and images. So we fabricated a chip for this, but anyway, so why do I want to work for video? And this is actually the focus of the research in my lab, because video is the biggest of the big data. If you think about it, video accounts for over 70% of today's internet traffic, right? So if you think of all the bits that flow through the internet, over 70% of those is to represent pixels. So it's a really significant bottleneck in terms of the system. So in general, when you're handling video, it's really important to compress well. What does that mean? That means that for the same quality of the video or image, I want to use fewer bits, okay? And there's just still a huge amount of video content that's out there, right? So if you just look at YouTube, for example, over 300 hours of videos uploaded to YouTube every minute. If you look at things like video surveillance, over 500 million hours of video is collected every day. And then, of course, Facebook is all video now, right? So there's just a huge amount of video that's floating through the system. So this is a continuing, growing challenge that we have. Another reason that it's important to compress video or to handle video is that the resolutions are getting larger, right? So these days, it's very easy to buy an Ultra HD television, for example. So you think about how much faster you have to process those pixels in order to decompress them in real time to play back that video. And then the same thing is when you're trying to capture the video, to process those pixels very quickly. And then finally, these days, video is like a must-have feature on your portable device. So of all of you sitting in the audience, how many of you have a phone that has video or can play video? Okay. How many of you would actually buy a phone that does not play video? Right, very few. So as a result, you really need to have it. But the problem, of course, is on your phone, you have limited battery capacity, right? You don't want to have these huge batteries because it's going to weigh down your phone. So you really need to have energy efficient processing of these pixels, and particularly for compression, right? So this was an interesting challenge that was coming up, particularly at the time. So just to keep in mind, the first iPhone was released in 2007. So it was like video was not a big thing on a phone, and even if you did have on the phone battery would die. So the question was, could we also make video processing much more efficient? We just saw, in the previous two slides, that if you can use parallelism, you can lower down the voltage, and that's a very effective way of saving energy. But the problem is that in video compression algorithms, it's actually very hard to find this parallelism. One of the reasons why is the way video compression works is that you're removing redundant information from the video, and this, as a result, causes parts of the videos to be dependent on other parts of the video. And so making that parallel becomes very challenging. So what you actually had to do was not just work on the hardware and the circuits, but now you have to start thinking about how can I redesign those signal processing algorithms to make them more friendly for the hardware. If I know that parallelism is a good thing from a hardware point of view, can I make the video algorithms or signal processing algorithms more parallel friendly? Of course, it still has to compress well. So that's what we did. We tried to look at different ways to make the algorithms more parallel, and so as a result, then we can reduce the voltage. which reduces the current, and then which reduces the power consumption. So this is a dye photo. So this is only actually in real size. It's going to be like around 3.3 millimeters by 3.3 millimeters, but it's the size of the dye that's doing this video processing. And as a result of doing this, you could actually reduce the power consumption of video decompression by 10x. So it's easy to say 10x, but then the question is, what does that actually mean? How does that feel like, right? So if I said you had 5 millijoules of energy, right? If I played it without doing these low power techniques, this is how much video you could play. Let's see, right? So for 5 millijoules, that's how much video playback you could achieve. But if you have 10x more, so if you're using these low power techniques for the same energy, now you can watch all of this video, right? And judging from the video date, you can guess when I finished my PhD. This is when the first Hunger Games came out, right? But then you can get a feel in terms of how important it is to extend the battery life by 10x. Okay, so this is what I primarily focused my PhD on, how to do low power video compression and decompression. But the key thing was when you start changing the algorithms or the signal processing algorithms, really you have to go and impact the standard or video compression standard in order for this to have effects. And so what a video standard is that, so if I compress video on, let's say, my iPhone, I want you to be able to decompress it with your Samsung Galaxy phone, right? So as a result, we need to have a standard that agrees in terms of how we do the compression and decompression. And so as it turns out, there's a large international standards body that does this type of work. It's comprised of many companies that come into agreement in terms of how to do this processing. So after my PhD, I went up and joined Texas Instruments, or TI. They were primarily sponsoring my research at MIT, and really we were working on what we called the next generation of the video standard, H.265 or HEVC. This is a successor to H.264, which is widely used in a lot of the internet videos out there and also all these DVDs. And the goal is to achieve twice the compression as H.264. So what does that mean? That means for the same quality video, I have half the file size. And so that's typically the goal here. So if you look at the different standards in the past, starting from MPEG-2, this is what you use for HDTV broadcast over the air. That was established in 1994. H.264 was 2x better compression than that, means half the file size, and now HEVC is another half. But the additional thing that we did was we actually also addressed the energy consumption. So usually what happens is that if you wanted to, half the file size, you have to do a lot more computation, and so the energy would go up by 4x. But now this time around, when we looked at going from H.264 to HEVC, right, we really tried to manage to make sure that the algorithms that we designed could really map well to the hardware, and so the energy increase was only about 50%, right? And so this is really important for the mobile devices. And also it's able to go much higher in terms of throughput, so you can now do Ultra HD 8K at 120 frames per second. So as a result, it's now widely used on many devices. So if you have an iPhone, for example, it does use, if you see the HCIF file, that's using HEVC for image compression. It's also used for a lot of the video compression there as well. And as Andres mentioned, then last year, we also got an Emmy. This is myself and my TI colleagues for this work, right? Okay, so that ends my term at TI. So the standard is over, so I'm trying to figure out what to do next. So I decided to go back to MIT to be a faculty member. So we still continue looking at next generation video coding. It still becomes a challenge, but really pushing forward, what we're interested now is not just compressing the pixels, but really understanding the pixels. So there's a wide range of applications out there where you don't just really want to watch the video, you don't just want to decompress it, but you want to extract the meaningful information that's in the video itself. Right? So whether this be facial recognition or in autonomous driving, when you're trying to have all these cameras on your car and trying to make a decision as to where to go, you can imagine that nobody really wants to watch the camera feed of a car. You just want to extract the meaningful information and take an action. Right? And so the question that we had is, since wherever you deal with video, you typically do compression, for the same energy and cost budget that you would allocate for video compression, can we actually understand the contents of the video for that same cost and energy budget? So can we make computer vision or AI or understanding of these pixels as ubiquitous as video compression? That's like the big overarching question that we asked within my research group. Okay, so the first question is, why is vision difficult, right? And so if you saw this image, right, I think you guys can all, even though you guys are all full from lunch, you can recognize that it's a cat, right? But if your computer saw it, and Xavier mentioned this morning, what it actually sees is a bunch of numbers. And this is a much more difficult task if I gave you a bunch of numbers and asked you, what is this image? Right? You can actually, if I gave you a bunch of numbers, these are basically the values of the pixels, this is still compressible. I can compress it based on the statistics of this number, but understanding it is quite a different challenge. So typically, computer vision would require much more processing than would be needed for video compression. So this is an interesting challenge now to have, right? So if we're trying to fit into the same budget, it's going to be quite difficult to do. The other thing I just want to also highlight is the concept of just deep learning and AI. So we have guys have a whole major on machine intelligence here, but just to understand the intersections of all these different technologies, AI is a very broad field, and then within that there's a concept of machine learning, and then within that there's brain-inspired machine learning, and then there's both spiking and neural nets, and then within neural nets there's deep learning. So the reason I just want to put this up is often people conflate deep learning and AI, and they're actually, deep learning is a very small subset of the whole space of AI, right? I just want to emphasize this. So in today's talk, I'm going to primarily talk about deep learning, but there's a wide range of other types of areas that could also benefit from efficient computing. So one thing I also want to address is, why is deep learning hot now? So actually a lot of these concepts have been around since the 50s, 60s, and so on, around for decades. So why has it really picked up now? So it's in the intersection of three main things. One is that there's a lot more data that's available now, right? So we talked about a huge amount of videos in YouTube, also images in Facebook, and then Walmart has also generated a huge amount of data. One significant thing is compute. Right, so GPU acceleration, because of Moore's law over the years as the transistors become smaller and more efficient, has allowed us to do a lot of this compute much more efficiently. Right, so there's a big combination of data and compute available, and of course some new machine learning techniques. But some would argue that these two things are very key, in particular the compute. Just to give you an idea in terms of where the instances that enabled this to happen. If you look at ImageNet, so this is what kind of started this recent wave of deep learning. This is from Fei-Fei Li's group at Stanford. They put together a challenge that basically is a training set composed of 1.2 million training images that are all labeled, right, into 1,000 different categories. There's also an object detection task here, but in general, the key thing, it's a large data set that's labeled, right? And then so you can train your neural network based on that, and they held a challenge every year. And prior to this, you need to have what we call handcrafted features. So a human expert would come in to, say, well, we're looking at edges. Edges are useful features to extract and design features based on that. But since the started use of deep learning, this is primarily through a contribution from here at University of Toronto. Through AlexNet, there was a huge drop in the error rate, and then since then that's been dropping ever since. And then 2015, deep learning actually beat human level accuracy. It's always important to point out that this human is one human at Stanford who's representing all of mankind, but nonetheless, it's a data point to have, right? So this is why people are very excited about this space. But the other important and interesting thing to note is that since 2012, which is when this whole trend started, there's been a lot more GPUs that have been used in the competition, right? So the number of entries in the competition that use GPUs basically increased until basically it's the default way of doing this type of processing. And the reason why GPUs do much better is that it enables more parallel computation. Right? It's designed, it's a better fit, it has a lot more compute power for this particular type of operation. And now actually these days CPUs are catching up as well. But in general, the key thing that's driving a lot of this innovation is having access to that very strong computation. So deep learning is used in a wide range of applications, of course, computer vision, speech recognition. So on your phone, your assistant there is using deep learning. Gameplay, right? So this was back in 2016. They showed that deep learning was able to beat the world champion at the game of Go, and that was thought to be one of the grand challenges of AI. I think very recently they also reported that deep learning can beat an expert at StarCraft. So. Then there's the medical space too. People are starting to use deep learning to help diagnose diseases. So for example, looking at different CAT scans or mammograms, looking at cancerous tumors. All right, so what are the opportunities in this space? So you can imagine, since this talk is about computing, it's really focused on the opportunities for computing. So if you look at this quote from Greg Diamos, basically said, today the job of training machine learning models is limited by compute. If we had faster processors, we'd run bigger models. And in practice, if we train on a reasonable subset of data that could finish in a matter of months, we could use the improvements of several orders of magnitude or 100x or greater, right? So if you can compute, if you can basically run bigger models, you can train on more data, and you can increase the accuracy. So what's limiting the progress of deep learning is actually the computation. Another luminary of the arrows basically referred to compute as being the oxygen of deep learning. So you really need to have more compute. And as I mentioned, the reason why we have GPUs now that run really fast, one of the reasons is obviously Moore's Law, but Moore's Law is now slowing down, right? So now it becomes a very interesting challenge for our engineers to design better computations without relying on the transistor getting faster, but coming up with better circuits and better architectures to enable this progress, this rapid progress in this space. Okay, so hopefully it's clear that there's a very tight connection between efficient computation and the progress of deep learning, right? But then secondly, there's also a lot of connection between computation and how we can actually use deep learning. So for a lot of applications, we might want to do processing at the edge instead of the cloud. Okay, so why would you want to do that? So one reason is privacy. So maybe you're collecting a lot of data about yourself that you don't necessarily want to share with the cloud. It might not be secure. Another application is in terms of robotics or in terms of latency, right? So sometimes if you have to send the data to the cloud, for the cloud to go make a decision, for you to then take an action, you might have crashed into something by that point if you're traveling, right? So you want to process again locally at near the device. You don't have this large latency. And of course, when you're dealing with visual data, sometimes you don't have enough communication bandwidth, right? So that might be quite limited as well. So now I'm going to talk about four different areas within my research group that really wants to move a lot of this compute to the edge and how we can go about doing that. So we're first going to talk about how do we build efficient hardware for deep neural nets, which is basically deep learning. But then there's many limitations to existing approaches there. So it's important to understand what the limitations are. If we look beyond the deep learning accelerator, how else can we speed it up? And then finally, there are things out there that are not deep learning related. So what are other compute opportunities out there that we can look at? So first I want to talk about efficient deep learning hardware, right? So as a very basic background for you guys, deep learning, primarily when you're applying it to image processing, it involves deep convolutional neural nets. What does that mean? So it means you take in an image, you apply multiple convolutional layers, which I'll explain next. When we're talking about deep, we're talking about from up to maybe even 1,000 convolutional layers. And they typically go from low-level features, which are edges, to higher-level features, which might be, if you're looking at a car, a wheel, or something, and so on. And then sometimes they're followed by fully connected layers. Now, if you're talking about where you want to build hardware to make things more efficient and run faster, you often have to look at the entire problem and then look at where are the bottlenecks. So where is the energy going? Where am I spending most of my time doing the computation? And that's where I want to build specialized hardware. So as it turns out for deep convolutional neural nets, it's the convolutions themselves that account for over 90% of the overall computation, so they dominate both the runtime and the energy consumption. Okay? And so what is in this convolution that makes it so complicated? Well, so let's walk through it. So first, if you start out with a 2D image or a feature map, and you apply a 2D filter to it, basically what you do is you take an element-wise multiplication of the filter with the image, and you sum up all the products, and then you generate one output value. And then basically, in a convolution, you just slide this filter across the image, and you repeat this computation multiple times. And this is pretty typical of just basic image processing. There's nothing special about this, and we've been doing this for decades. What makes deep learning particularly challenging is that we increase the dimensionality of this computation. Right? So rather than just sliding a 2D filter across another 2D filter, what we're actually doing now is increasing the number of channels. So we have a third dimension, right, which is called channels. And if we use Alex as an example, we get 3 to 192 channels. And so now you're doing these 2D convolutions on each channel, and then you have to add them all together to generate one output. So you can see the dimensionality of this problem is already growing. In addition to that, we don't just apply one filter to the image, but we apply multiple filters, right? And the number of filters that we can use, well, if you use AlexNet as an example, again, we're talking about 96 to 384 filters. And each of these filters, when you apply it, will generate one output channel, right? And then, of course, in general, we want to process more than just one particular image. We want to process multiple images, right? So multiple images input as a multiple images output, right? So that's just like a lot of processing in general that's going on. And then typical number of input things that you're processing together is what we refer to as batch size, between 1 to 256. So, okay, if you didn't follow all of that, the main thing you should take away is that it's hundreds of millions of multiply and accumulates per convolutional layer. And as we mentioned, you can have, up to 1,000 of these types of layers, right? And this is just to process a very small input image. Typically, in these examples, we're talking about an input image of around 200 by 200 pixels, which is very small, right? That's a lot of computation for a lot of data. But there's some things that we really like about this. So one thing is that it exhibits high parallelism. High parallelism is possible because really all this is actually doing is a bunch of multiply and adds, and they can all happen in parallel. They're not tightly related, right? So high speed is possible. The real challenge, as it turns out in hardware, is not the compute itself, but how do you deliver the data to this multiply and accumulate engine, right? So let's walk through this together. So to do any multiply and accumulate, you actually need to have 3 inputs: the filter weight, the image pixel, and the partial sum, and you'll generate one output. So that's a 4-to-1 ratio in terms of memory access versus compute. Then in terms of the amount of energy it takes, well, if you look in the very worst case, if this data is read from DRAM, for each of these accesses, we're burning 200 times more energy per read access or write access than a compute. So it's a 4-to-1 ratio in terms of the number of accesses, and then each access is 2 orders of magnitude more expensive, right? So in terms of, in the very worst case, if you look at AlexNet, we're talking about 3 billion DRAM accesses, right, for about 700 million max. So that's something that we really need to address. But again, there's some opportunities to avoid reading these things from very expensive memories. We call it basically input reuse. And what do we mean by that? So if I read this data from very far away once, and I read it, can I use it many, many, many times so I don't have to read it again? So I can amortize that cost of bringing that data close to the compute, right? So there's multiple opportunities for this. So when we talk about performing a convolution where we slide this filter across the image, we have what we call the opportunity for convolutional reuse, which means that the same pixels and weights are going to be used multiple times, just in different combinations, right? So it means if I move those pixels and weights closer to the processing engine, I can reuse them multiple times. The other reuse opportunity we have is what we call image reuse, which is that I'm going to apply the same filter to multiple images, and so that means the pixel here can be reused multiple times across filters. And then finally, we have filter reuse because I'm processing multiple images. Right, so the same weight can be used many times across multiple images. Right, so these are all properties that we can exploit in order to save ourselves some energy. Just at a very higher level, in terms of the type of hardware that we tend to build what we call spatial architectures. The idea here is that for each of these little processing elements, I'm going to move a very small piece of memory beside the multiply and accumulate. And why is that? This very small memory is going to consume very little energy. But of course, the challenge here is that this memory is very small. We're talking about 0.5 to 1 kbytes of memory, which is almost nothing, right? So what you want to do is try to figure out, okay, I'm going to have these very small memories. What data should I move there? And then also all of these processing elements can talk to each other. So if they can share data, it's actually cheaper than going to that expensive DRAM. Okay, so if you take anything away from this, the main idea is that the data movement, moving data around the system, is very expensive in terms of energy, right? So if I do 1 multiply and accumulate, let's say it's 1x in terms of energy, reading from that tiny memory is also 1x. If I want to read from my neighbors, it's going to be around twice the energy. If I read from a larger memory, it's going to be 6 times the energy. And if I go to the off-chip memory, it's going to be 200 times. Right? So the main idea is that I want to keep as much data at these very small memories as possible. Right? So it's really cheap to read them. But the problem is these neural nets are very large. So the question that we have is that, how do I take large chunks or chunks out of this very large neural net, move it into this very small memory, and then use it multiple times? Right? And so there's different ways that people have done this. One is that they take the weights of the filter themselves, and they put it in the very small memory. This is what we call weight stationary, because the weights don't move. And so when you're doing all this computation, your filter doesn't move at all, right? So it's very cheap. The energy to move the weights is very low, but then you can see the pixels and the partial sums, all the other types of data move around the system. So it becomes very expensive. Another option that people have is what we call output stationary, that partial sum. So when you're trying to accumulate values, that data type, it's going to be read and written from this very small memory as well, locally in this device. And the reason why that might be better is because you're doing both reads and writes. So both the reads and writes are going to be very cheap because you're holding the partial sum in the small memory, but now the pixels and the weights flow all over the place, right? Okay, so then in our group we tried to look at, well, I don't want to always favor the weights or favor the partial sums. Can I really account for all the different data types? I won't go into the details, but the idea here is that basically we allocate one row of the convolution to each of the processing elements, and then you can do a lot of data reuse there. And the key idea is that if you look at all the different types of data in the neural network and try to minimize the energy of all the different data types, then you can overall minimize the overall energy of the system. Let me just go here. So this is probably the best way to show it. So if I look at where the energy is actually going in the system, you can see the couple of different configurations. So if we look at the weight stationary case where I didn't want the weights to move at all, you can see the green part here is very small, but the energy for the partial sums and the pixels are much larger, right? And then in this output stationary case, I'm really trying to reduce the energy of these partial sums. So the red part's really small, but these green and blue parts, so the weights and the pixels are also growing. And then so the approach that we proposed was looking at all the different types of data movement. So all the different types, and then as a result, you get the best overall energy efficiency. So this is about 1.4 to 2.5x lower than all the other cases. So the main idea here from an engineering standpoint, when you're looking at these systems, is you're trying to think through, well, if I don't ever want to just optimize for one type of data, but you want to optimize for all types of data in the system. You don't want to just bias for one particular given approach. Some other things that we factor in and we can look at from the hardware point of view is that if there ever are zeros, right? So we all know that 0 times anything is 0. Okay, everyone's awake. Okay, so, right? So then as a result, you don't need to perform that kind of multiplication. So you can skip that operation and you can save the energy related to that, right? The other benefit of having zeros is that you can actually use what we call run length coding and compress the data. Right, so you can avoid sending those zeros. If I have a lot of zeros, rather than sending 10 zeros, I can just say I have 10 zeros, rather than saying like 0, 0, 0, 0, 0, 0. You can just say I have 10 zeros and skip signaling all of those. So that gives you also about up to a 2x compression. Right, so all of this, we incorporate this into a deep learning custom chip that we call Iris. And just to give you guys a feel in terms of, we talked a lot about data reuse, what can you actually achieve? So let's say you needed to process 4 images for AlexNet. It would take about 2.6 billion computations. Usually that would require about 24 gigabytes of access to do all those computations. But because you're exploiting all this reuse, meaning reading from very small memories and sharing data amongst all the processing elements, you can actually reduce the number of reads to about 208 megabytes from that buffer and then 15 megabytes from off-chip. Right? So the idea here is, again, you're trying to reuse. If you can bring data close to the compute and then reuse it multiple times, then you're moving data less, and then you actually consume much less energy. So compared to, I don't have that slide, but compared to a mobile GPU, this is about 10 times lower power, right? Because you've reduced how much data that you have to move. Okay, but let's take a step back. So the whole point of this was to reduce energy consumption, right? So let's say we're trying to compare 2 different solutions or multiple solutions in terms of both energy and accuracy, right? So, originally if we looked at the old way of doing computer vision with those handcrafted features, they can actually be quite efficient, right? So hog feature, this is histogram of oriented gradients, was basically a well-known feature that people used for computer vision before 2011. Okay, and it consumes very little energy. So actually, in fact, it consumes less than video compression, which is pretty neat because that basically tells you that for the same energy of compressing the video, you can now understand the content of the video, right? But the accuracy, so shown here, accuracy in average precision for an object detection task is going to be less than 40% in terms of average precision, or 40. We know that's very exciting. We can go to AlexNet, and then we can basically almost double the accuracy. And if we go to, so this is AlexNet's type of deep learning, and then if we go to VGG, which is an even larger neural net, we can get even higher accuracy, right? So we can push in this horizontal direction. But the issue is, if we look from the energy point of view, so this in the horizontal direction is a linear scale. If we look at the vertical scale, that's an exponential cost, right? So AlexNet is actually 300 times more energy higher energy consumption than HOG, and then VGG is almost, 10,000 times higher. So if I were to ask you, I'm going to give you an app on your phone that is going to be, twice as accurate for computer vision, but it's going to drain your battery 300 times faster. Are you interested? Right? So battery is such a critical component, right? So really there's something that needs to be done in order to reduce the energy consumption still. And this is with, I want to highlight, this is with custom hardware. We still have this problem, right? So what this means is that you can't just solve this problem from a hardware point of view. We now need to move up and look at the algorithms that are being used to process these or to do this type of computation. Can we change the computation to make it more energy efficient? Right, so our team at MIT spent a lot of time looking at all the different ways that people have been trying to make deep learning much more energy efficient, both with coming up with new hardware and then also coming up with new algorithms. Okay? And so in case you're interested in this space, we have a bunch of tutorial slides available on our website and also some overview paper that you can take a look at. But the key thing that we noticed in doing this was that actually there's a lot of challenges that actually remain in this space in terms of understanding how to design the algorithms and the hardware together jointly. Okay, so there's still a lot of open challenges in this space. Okay, so now I'm going to talk about, so there's a lot, as I mentioned, a lot of work that you can do to speed up or make your deep learning more efficient. But sometimes there's going to be opportunities outside of deep learning to make the deep learning more efficient. I'll explain what that actually means. So we're going to talk about this in the context of super resolution. So what does super resolution mean? Well, what super resolution can do is that basically it allows me to transmit or send to you a low resolution video, and then on your device, let's say, or either on your display or your phone, you can generate a high resolution image on it, right? So that's pretty good because that reduces the amount of bandwidth that we have to transmit. So it can be thought of as a kind of a form of compression. The other reason that you might want to use super resolution is that the screens are getting larger. Right? So you can easily buy an Ultra HD television these days, but actually a lot of the video content, a lot of the movies that you watch out there are still in just HD, or maybe even lower if you got from a couple, many years ago. Right? So you need to generate higher resolution video in order to fit that screen. You just don't want to upsample it because it'll be very blurry. You want to have the high quality. So super resolution is a very important application important tool for these type of applications. The challenge is, of course, these days the state-of-the-art approaches to do super resolution involve deep learning. And I just want to highlight that previously all that work that we talked about, we were talking about deep learning for a very small input image of around 200 by 200 pixels. But now we're talking about applying super resolution. If I want to generate an Ultra HD video from an HD video, that's going to be even more compute than what we saw before. And that can be very challenging and very costly. Right? So again, especially if you're doing this on your phone, you can't really afford to have that much compute. Even if you're doing it on your television, you don't want to strap on this huge NVIDIA GPU to be running your television either. So it's computationally very expensive. So what we did was we tried to think of, is there a way that we can actually speed up deep learning that actually doesn't involve changing the deep learning algorithm? So can we come up with a framework where you can take in any super resolution algorithm, any compressed video, and then generate real-time super resolution video at a much faster rate? So then I had to go back and think back to, how does compressed video actually look like? So if you think, maybe if you're from an image processing point of view, if I gave you some compressed video, primarily the way you would look at it is just a group of pixels, right? You just watch the pixels, it looks great, so video is a stack of pixels. But if I think back to my video compression times, we actually spent a lot of time, like an enormous amount of time, trying to think of different ways that we can find correlations between different pixels in the video itself. So which pixels look like which pixels, and if they look the same, then I can remove the redundancy between that. I can use one pixel to predict the other pixel. Right? And that basically what that means is we're trying to find a lot of structure in the video. So for example, in motion compensation, if you look at 2 frames of a video, they actually look very similar. So rather than sending all of these pixels, after sending these pixels, I can just say rather send an instruction that says copy some pixels from the previous frame. Right? And that's going to save me a lot of data that I have to send out. I mean, that's basically the fundamentals of video compression. So the question is, can we exploit this representation of compressed video to speed up super resolution? And then, of course, the answer is that you can. So rather than running super resolution on every single low resolution frame, so if this is a low resolution, I'm going to run super resolution on every single one. Rather than doing that, what you can actually do is run super resolution on one frame, and then use this information about the correlation between the pixels that's already built into the compressed video to quickly transfer that information to all the other frames. And so then you can quickly generate a bunch of high resolution frames, and you only had to run that super resolution algorithm once for a set of frames. Okay? And so this transferring approach is actually very, very fast. Right? It actually involves what we call a bicubic interpolation, so that's almost nothing. There's no neural net involved with this transfer. And then in fact, sometimes if there's no movement, you can imagine if there's absolutely no movement in the frame, you can have what we call a skip flag, which means just copy the whole entire frame to the next frame. Right? Then there's no processing whatsoever. Right? So in fact, basically, if I transfer n frames, I get an n frame speed up, basically. So we evaluated this approach on a bunch of videos. In particular, the videos that we were looking at are the videos that were used to develop that HEVC standard. Right? So they are very wide in terms of diversity. If we look at the peak signal to noise ratio, that's a quality metric that people use, you can see that SRCNN with this fast transfer approach has the same quality as without doing it. This is for if you transfer up to 4 images. And similarly, if you transfer up to 16, you get a little bit of a loss, about 0.2 dB, but not too much. Right? But you're having a 16x acceleration. Right? So usually these things are better if you can actually look at the video themselves. So shown on the most left-hand side, this is what super resolution would look like if you ran that SRCNN approach. And so the best way to look at these is like look at the text. You can tell that like the text here is much more blurry than the text here. So this is the original baseline approach when you run super resolution on every single frame with the CNN. On the right-hand side is where you do the most simplest thing, which is just do quick interpolation. So this is very low cost in terms of processing, but you can see it's more blurry as you focus on the text. So what happens is this fast SRCNN approach that we took, where we're just transferring the pixels, this middle approach has the same quality as this SRCNN approach, but it's just as fast, or the computational complexity is the same as this bicubic approach. So then as a result, you're getting both the benefits of the quality as well as the speed. Okay? So if you're interested in this, we have the code online. But the main message I have here is that, so sometimes, actually a lot of the times, people really focus on trying to improve the processing of deep learning. But you can actually look outside of the module where you're doing deep learning and find other opportunities to speed up the processing. For example, here, it's the format of the data itself, or the structure of the data itself. So exploiting this relationship in the compressed data. All right, so that's all the stuff with deep learning, but there's other stuff that you can do beyond deep learning that's also interesting to do processing at the edge. So one of them is looking at enabling autonomous navigation, particularly for very small, kind of bottle cap sized drones. So this is in collaboration with Surtesh Karaman, who's a faculty member in the Aeroastro department at MIT. And so the idea is that if you have these very small drones, you can't slap a very large battery on it. It's going to just basically make it fall. Right? So how can you actually make this autonomous itself? Right? You can imagine this could be useful in applications like search and rescue, where there's a big disaster zone, there's an unknown environment, and you need to have these drones to navigate that space autonomously. So we worked on developing a chip that does what we call localization and mapping. And I'll just give you an idea of what that actually means. So localization and mapping, basically the idea is that I give you a bunch of images. I also have an accelerometer, or IMU, on the actual drone itself that has accelerometer and gyroscope, and then based on that, I fuse the information and figure out where I am. So for example, you can imagine here's the visual data that's coming in, and you're trying to estimate where you are in 3D space, okay? At the same time, if you have an unknown environment, you also want to create a map of that environment, right? So this is a very important operation that typically happens for autonomous navigations, but you can also imagine this is also used in augmented reality and virtual reality as well to understand where you are in the space based on your sensors. You might also be familiar with the term SLAM, so this is a subset of SLAM. And so how does this actually happen? Well, you take in some camera input, and you take in your IMU input. Your camera input, basically what you're doing is that you're capturing images of your surrounding as you're moving. And what you can do is you can try and identify certain objects or certain features in the images as you're walking. That gives you a clue in terms of how you're actually moving, right? So, as I'm moving this way, if I'm looking, I can see that this corner here is approaching me. And that kind of tells me which way I'm actually going, that it's actually approaching me. So that's what you're doing on the images, the type of processing you're doing there. And then in terms of the accelerometer, that's also giving you some information about your pose and your trajectory, and you're trying to summarize that information as well. And at the end of the day, you have to fuse these two types of information together, right? And they might have some inconsistency, so depending on where I'm looking, some parts might be occluded in space, so I need to resolve those inconsistencies. And this is a very large optimization, which I won't get into using a factor graph, but there's a large optimization that tries to, based on all the things I've observed in the world, how can I figure out where I actually am to, kind of try and satisfy all the things that I've observed. Okay, so again, the main takeaway from that is we mentioned that, if you read these things, if you have to move data around a lot, it's very expensive. So we have to try and put them all on a very small chip. So we want it to be all fully integrated. We want to do all the processing in that very small chip. So I think we showed here, all on this very small die. We want to do all of that processing that we just talked about locally so that we can really minimize the energy consumption. And then one of the key things here is that you have to do a lot of compression, because if you want to store everything on chip, you really have to make sure that you're not taking up too much memory. So for example, all in all, by exploiting both compression and sparsity, which means exploiting the zeros, we reduce the amount of storage by 4x. So here's an image of the test chip itself. In terms of how fast it can go up to 170 frames per second. In terms of what it's capturing, it can update its state, its estimate of where it is at every 90 frames per second, and it consumes around 24 milliwatts. If you want to go a little bit slower but more in real time, so at 20 frames per second, it's consuming around 2 milliwatts of power, which is pretty low. So just to give you an idea in terms of how much power your phone consumes, it's around 1 watt, right, in terms of processing. So this is around 500 times less than that. Here's a demo of the system. Right, so, okay, I don't know if you guys can see. So here is the chip running itself. Right, and it's consuming, you can see about around 10, 13 milliwatts in this example, and then you can see that based on these inputs, it's trying to estimate where it is in the 3D space. Okay, so another thing that we're actually looking at, again, this is an autonomous navigation space, is that once you figure out where you actually are in the world, you have to decide where to actually go, right? And so in particular, if you're looking at a kind of a search and rescue mission, you want to basically go where you can get the most information about your unknown environment. So you have to compute that in real time. So what this is doing is it's looking at computing what we call the Shannon mutual information. And so where it shows as bright yellow, that's where the car is going, because that's basically where you can go to get the most information, right? And the faster that you can compute this mutual information, the faster you can explore the space. So again, if you think of a search and rescue type of application, right, the faster you can explore, the more people you can find, for example. Okay? So again, doing this computation efficiently on the vehicle is very important. So two last things. So one thing is that in order to do a lot of this robotics and interacting with the world, we don't just want to look at it from a visual standpoint like a 2D image. We actually need to know depth as well. You need to know how far away things are, right? And a very common way of getting depth estimation is what we call time of flight. So I send out a pulse of light, maybe with a LiDAR, and I wait for it to come back. And so however long it takes for you to come back, that tells me how far away that object is. The problem with that is, or the challenge with that is that typically this illumination, this sending out the light, can cost a lot of power, right? So for example, for just about 8 meters, you're talking up to 20 watts of power, right? And again, think about your phone, it's like a 1 watt kind of envelope. So one question that we had is, can we actually use various computer vision techniques to reduce how often we have to signal this laser, right? And so in particular, if at time 0, I signal the laser and capture a 2D image, can I then guess or estimate what the depth is going to be if I only had the 2D image on for the other components, right? Just fill in this depth, right? Now the challenge is, that way basically my depth sensor is on for less, but the challenge here is that then the computing or the processing that I need to do to guess these depth estimations should not be too expensive, right? Otherwise you cancel out the benefits of this depth estimation. So we're able to actually run this computer vision algorithm on a Cortex-A, which is a very small processor on a phone, and do VGA at 30 frames per second at under about half a watt. Okay, and so just to give you an idea against the quality of it, so here's the RGB image. Here's the ground truth, so if I constantly measure depth at every single frame, this is how it looked like. And then if I only keep my depth sensor on every 9th frame, this is how it would look like. And so I'm recovering so basically I have a mean relative error of like 0.7%, but in general, the quality is about the same. Right. So this is another way that you can actually, by using efficient computing, you can reduce the cost of sensing your environment. Right? So it's not just reducing the cost of your processor, but reducing the overall system power. All right, so then one last project that we've been looking at in groups. So we've looked at computing for AI, we've looked at computing for improving image, video compression, computing for robotics, but we've also been looking at in terms of the health space. So this is in collaboration with another professor, Thomas Helt, in the Institute of Medical Engineering and Sciences at MIT. And so together we've been looking at the issue of dementia. So we know that dementia affects 50 million people worldwide today. And then the World Alzheimer's Report expects that to grow to 75 million in 10 years. And so in order, one of the key things to evaluate this is doing a neurophysiological assessment. And these are typically time consuming and they require a trained specialist. So you have to go to the doctor's office or go to a clinician and they might ask you, for example, a bunch of questions like, what is the year, season, date, where are you now, what state, what floor, count backwards. You might actually also have to do this, clock drawing test. And the issue with this is that this is all very expensive, so you don't go in often, so the amount of measurements you have is very sparse. It's mostly qualitative, so it really depends on the person who's administering the test on you, and so there's going to be high retest variability. So if I do it again, there's going to be a lot of variations in the evaluation. What they've recently found, though, is that in conjunction with these tests, you can pair it with eye pattern movements, which can be more quantitative in terms of evaluating the quality of a person's mental health. And you can use that to evaluate the quality, the severity, or the progression or regression of a disease. So for example, if I'm testing out a new drug, can I see if it's actually helping the disease itself? So for example, shown here in this display, this is the reaction time of the eye movement. This is for a normal elderly patient. This is for a patient with mild cognitive impairment, and then in a patient with Alzheimer's disease. And so you can see that when you have Alzheimer's disease, the reaction time has a much higher variation. Right? So this is a much more quantitative way of doing these tests. Now the problem with these tests is that typically you need to go into a clinical setting once again to do them. Right? So they require either these very high-speed cameras that cost hundreds of thousands of dollars, or you need substantial head support to strap the person in, right? Because you can't afford to have them move too much. You might also need IR illumination to light up the eye so you can really detect where the eye positions are, right? And so these clinical measurements of this saccade latency, or eye movement that we're talking about, is typically relies on this very specialized and costly equipment. So what we're trying to do in our lab is see whether or not we can replicate those tests on your actual phone, right? So for example, if you give a test shown up here, right, I have an eye pattern, I ask the person to look at, where this yellow dot is, and they move their eyes. So their reaction time, which is what we call saccade latency, will tell us some information about their mental health, right? So we get a saccade latency distribution here. And so the key idea is that using these consumer grade cameras on your phone, can we actually develop algorithms so that we can replicate the quality of these latency measurements that we would find instead of using those very high speed, very expensive IR illuminated cameras that you have in the clinic. And so indeed, in fact, it is possible. So if we look at the distributions that we obtained from an iPhone versus this phantom camera, which is 100 times more expensive, they're very similar, right? And so what does this mean? That means that now you can move this evaluation into the home. You can do it more frequently, and it's also going to be more stable and provide the clinician more information about the patient's state. Okay? All right, so that's a whole bunch of different projects. Hopefully it's very clear that computing is very important. So basically what I want to get through is three things. So one is the expertise in electrical and computer engineering intersects with many fields. I just gave a subset of them here, right? So we can see that it affects just in computing in general, obviously, but video compression, artificial intelligence, in particular deep learning here, robotics, and healthcare. So it's really something that can permeate many fields, as long as you need to do some computing, which is obviously the case. The other thing I just want to emphasize, it's important to have a broad foundation because it lets you adapt to your changing environments, and it allows you to be prepared for any emerging opportunities that you might not have thought of. So if we go back to when I first started as an undergrad, like I said, I wanted to do more image signal processing stuff, but then when I went on PUI, there were no opportunities there, so I jumped into circuits, right? And I was only able to do that because I took some circuits classes, right? And then as it turns out, there's a lot of interesting opportunities at the intersection of both circuits and signal processing. So having a broad foundation, even if you take one class, you're not too into it, you shouldn't completely give up on that space. It might be useful down the line, okay? So broader helps. The other thing, just in general, that we've noticed for everyone's career trajectory, it's really important to do one thing or a subset of things well, rather than doing a whole bunch of things, but then none of them having impact, right? So often I get asked in terms of, what do people look for, let's say when you're applying to grad school, right? And so one thing that we look at is, were people able to take, the opportunities that they had and make something of it? Were you able to, if you worked on a research project, were you able to generate outputs? It's not that I worked on, 5, 6 different research projects, but then I have nothing to say for it, but that I actually take my opportunities, whether it be a research project or working at a company, and really making an impact there. That's what people are looking for. So even if it wasn't in the exact same skill set that we needed for this next opportunity, we can see that this person is someone who really pushes things all the way through, and then they can learn new skills, but this is the right kind of attitude that we're looking for, the right kind of grit and skill set that we're looking for. Okay, and then finally, I just want to acknowledge my students. A lot of this research would not be feasible without the help of my students. Obviously, they did actually most of the work, and then our sponsors as well. And I think that's basically it. So yeah, if you're interested in any of the overview stuff for deep learning, we have a lot of references for that. And that basically concludes my talk. Thanks. Right, so I'll just repeat it for the video. The question is basically, how do you perform research with limited resources as compared to industry, which has, relatively speaking, much more resources than you might have in academia? So I think what you have to do is you try to pick your problems carefully, right? So for example, you try and define questions or problems where it's not just like a brute force search, for example. It's not just based on sheer willpower or sheer monetary reasons why you can solve it. So you have to think more deeply. That's why. So you use your brain as the weapon. So you find a project, you think of an opportunity where you can, what you have that industry might not have is that you don't have as much tight deadlines. So you have the liberty of thinking more broadly of the area, and then you also trying to think more deeply in terms of problems. So really trying to think through, what are the different ways that I can approach this that's not a brute force way. Right, a much more elegant way. Or, some of the things that we try to do is look more holistically at the problem, so not just solving some small problems, but we can really think end to end in the overall system, and what are the challenges at the interfaces, where typically maybe that's less feasible in industry when things might be a little bit more siloed. So hopefully that answers your question.
We have time for one very short question.
So your question, so I'll just repeat it for the camera. So your question is basically, when you come up with when there's a research problem that people have been exploring for months or years, how does one go about tackling it to try and solve it? So I think generally speaking, I guess the way that I look at research is I always try to pick problems where I find that something in my background would give me a more unique perspective on that given problem, right? So for example, in the space of video coding, primarily the people who were working in that space were looking at how to improve compression. But I was trying to come at it from a different lens because I've been working on reducing power consumption and looking at circuit design and how that goes. And so from that different lens, it opens up a lot of interesting opportunities in that space that people have not seen before. I would say similarly, in a lot of these projects, you can see the intersection of, in the deep learning space, but again, a lot of people focus on the algorithm, so we started looking at the hardware point of view. Now there's a lot of people also looking at the hardware point of view, and so we're trying to think, what are the interactions between the two, right? So I think it's really more trying to identify the problems that you feel that you can contribute to and offer a different lens to make an impact. And that's why often interdisciplinary research is very exciting. You learn a lot, first of all, and usually a lot of the open questions actually lie at the intersection of multiple fields.
Thank you very much, Professor. That was a very wonderful talk. Just as a reminder, we will have a networking session at 5:30 in our house. Professor Steve will be there, and you can ask as many questions as you like. On behalf of the Division of Engineering Science, Professor, I'd like to present you this gift.
All right, thank you very much.